This is Pre-Calculus B, Unit 2, Lesson 7, Modeling with Trigonometric Functions. So this is one of the target points we've been getting to. The purpose of mathematics, one of the major fields of mathematics, is something called mathematical modeling. So we take a real-world situation. For example, you might record the average daily temperature over a period of time and model that, or you might model the path of a hurricane to predict where it might make landfall. You might model the impact of smoking and how much smoking affects maybe the occurrence of lung cancer. And there's all kinds of mathematical modeling we go to in order for us to be able to make predictions, to help us to understand causes and effects and magnitudes of effects. So we're going to model in this case classes of functions that are trigonometric functions. So we can now recognize, because we've studied the shapes, we can recognize the shapes that are made by the various functions. So let's say, for example, this table of values. I have an x and y table on the screen, represents some data I've collected. And immediately I notice that there's kind of a sinusoidal shape to this thing. It's shifting up, and then it's shifting down, and it's going back up. And it appears that a sine function would work. Now, in fact, it may not be sinusoidal. It might be something else, and there is something worth considering there. So anytime you think a model might fit, it's important to consider how well the model fits, but also consider what each of the variables in the model represent. Now, in this particular case, I'm going to go with a sinusoidal fit. And we're going to walk step by step. This is very similar to what we did in the last recording. So I'm going to say, well, I think this is built on sine x. So I'm going to say sine x. Now I notice that the shape, the general shape, the up and down motion of the shape is good. By the way, in Desmos, if you use Desmos, click the zoom to fit button in order to zoom it to an ideal location. I've already kind of fiddled with the zoom window here to make it show what I want it to show. But that zoom to fit feature is nice. So I need to set my midline, right? One way to do that is to consider, well, what's the highest point? 77. What's the lowest point? 46. Halfway between 77 and 46. I'm going to do this in my head this way. 77 minus 46 is 31. Half of 31 is 15.5. 15.5 plus 46 is 61.5. Okay, so I'm going to say plus 61.5. Okay, and hopefully if I've done that right, that is the midline. The midline. So the equilibrium point, if you're talking about physics. By the way, one of the things that can be modeled very well with a sinusoidal function is oscillating masses on a spring or a pendulum that swings back and forth. Okay, so we've got our center point. Now we need to set our amplitude. Now our amplitude was kind of already figured out. Our maximum distance was 31, right? And half of 31 is 15.5. So it sounds like the magnitude is 15.5. 15.5. There we go. That's approximating the magnitude, the amplitude. Okay. Now we need to approximate the period, and this takes a little bit of fiddling. Look for points that are in phase. This point seems to be about the same height as this. They're in ascendancy. They're coming up. And so this seems to have a period of 12. Okay, you remember the trick for setting a particular period? And you multiply x by 2 pi, which converts it to a period of 1, and then divide by the period that you want, 12. Okay, now it's got the right period. Now it looks like I need to phase shift a little bit. The peak occurs about 1 to the right. So I'm going to put a parentheses around the x. And I'm going to say minus 1. And there we go. We've got a pretty good fit. It's not perfect. We might try fiddling with it a little bit here. But that's it. Now, That said, I do want to show you a really neat feature with Desmos. Desmos will do curve fitting, as your TI-84 calculators, graphing calculators will, but I love the curve fitting in Desmos. Here's how you do it. You'd say Y1, okay, which is Y1, and then tilde for takes the value of, and then you put in your formula. So A sine B times X minus C plus D. And I forgot one thing, X, it needs to be X1. There we go. And it will model this data here to fit. And notice it's graphed now, it's the blue graph. And it fits even better than our data. It's very similar, very close. But it's giving a correlate. R squared is what we call the variance. It's how close a fit is. This is more than a 99% fit, so this is pretty good. But it's saying the A value is 15.1, not 15.5. The B value is 0.528. Mine was 2 pi over 12, which is 0.5235. Okay, so they're very similar. The C is 1.03, so the right shift is 1.03, not just 1. And the vertical shift is 62.1, not 61.5, so it's vertically shifted a little bit more. Okay, which is kind of an interesting one, right? Now, you don't need to know this, but it's really nice to know that you can use this. It uses the least squares regression method for fitting the curve. So, really kind of cool. Now, I want to show you one more way here. I could have tried to fit this with some other function. Okay, so for example, maybe I would determine it goes up, it goes down, it goes back up. Maybe it's cubic. So I could do this. Y1 takes the value of A1 plus A2 x1, that's linear, plus A3 x2 x1 squared, that's quadratic, plus A4 x1 to the third. All right. And you can see the cubic function has an up and down and back up formula. But you can clearly see that it's actually a sinusoidal fit is much, much better. I just did that to show you that when you think it's sinusoidal, it might not be. There are many kinds of formulas you can use to fit data. But you want to fit the one that fits best. Now in this case, it's leading in that the original problem may say this is a cyclical thing, like maybe this is weather over a year, and I know that the typical weather patterns repeat themselves. The seasons, they come and go. Summer keeps coming every year, winter keeps coming every year, and so forth, and there's a cyclical pattern, and that definitely suggests sinusoidal. All right, so that's the big idea. That's curve fitting.